Today we are talking about projectile motion. Projectile motion refers to any object that is dropped or thrown, is moving through the air in some way. That's because the definition of a projectile is any object on which only gravity is acting. So again, a projectile is an object on which the only force acting is gravity. That means the only directions being pulled is down. That means something that we drop could be a true projectile, say a rock, a heavy rock where air resistance plays very little part on it. But if we were to drop a feather on Earth where there's plenty of air, that would not follow our rules of projectile motion because there would be so much air resistance. So for this unit, we are going to be saying constantly air resistance is negligible or air resistance is not present. Or don't worry about air resistance or ignore air resistance. All that means the same thing. So let's take a look at a free body diagram. A free body diagram is a graph or a diagram we use, not a graph, diagram we use to show forces acting on an object. We'll get to these when we get to forces. In a projectile situation, how many forces are acting on the object? One. And what direction does that force point? Down. So we would simply draw in a downward arrow and label it the force of weight. Again, we'll get to this again in the future, but it's important now to realize that any object that is a projectile is only being pulled in one direction by gravity, and that direction is down. Let's take a look at an object falling. Let's see it slower. And even slower. Take a look at how far it moves each frame. Can you see that the distance it moves each frame is getting farther and farther? So this is the question. Does the ball travel the same distance every second? And like we said, we were doing it by frame because if we did it per second, that would be a really, really high tower we'd have to drop the ball off of. And the answer is no, right? The ball moves farther and farther every time interval when it falls. It is accelerating downward. And here we have a dot diagram of a ball falling. Does this ball fall the same distance every second? Absolutely not. The ball travels farther per second as it falls. It moves farther every second when it's falling. Notice, the distance between these dots is very small. The distance between these dots is much larger. There was acceleration there. So what would the velocity time graph of this ball look like? As it falls, it gets faster and faster, right? As it falls, it gets faster and faster. And in fact, we can get the acceleration of this ball using this graph. Remember that to get the acceleration off a velocity time graph, we're going to get the slope. So let's choose this point and this point. So rise here would be negative 20 over run, from negative 10 to negative 20 would be negative 10 divided by a run of 1 to 2 is 1 second, so negative 10 meters per second per second. It accelerates by 10 meters per second every second, and thus the acceleration is 10 meters per second, or 10 meters per second squared. You may have heard that the more precise measurement is 9.8 meters per second squared, and that's absolutely true. But for this class, we're going to use 10 because it makes the math easier, and it won't make your calculations that different. So let's create an acceleration time graph. That's new. For an acceleration time graph, we're simply going to graph the acceleration. And the acceleration the whole time is 10, negative 10 meters per second squared. So the acceleration is negative 10 meters per second squared the whole time, the entire time, which means we can use our kinematics formulas. So you remember our definition of acceleration. Acceleration is the change in velocity over time, and we can rearrange that to give us that Vf equals Vi minus At. And thus, if we want to, we can, if initial velocity is 0, such as when we're dropping something, we simply multiply acceleration times time to give us our final velocity. So if an object is dropped and falls for 3 seconds, 3 seconds times the acceleration of 10 means it will be moving at 30 meters per second downward, or so maybe negative 30 meters per second. But what if instead we want to know how far the ball has fallen? Remember, we had one formula for how fast and a different formula for how far. For how far, we're going to use the 1/2 AT squared formula. Now, once again, notice that the ball gets farther and farther apart every second. We can see this as the t is squared in relation to the distance. The distance gets farther down as a function of the square of time. That's why we see the bigger and bigger gap between every dot. So, once again, we have two equations, Vf equals Vi plus At for how fast, and 1/2 AT squared for how far. Let me make one more note about the 1/2 AT squared formula. If the ball is dropped, if an object is dropped, initial velocity will be 0, which means the equation, this part will go away, and we'll be left with just 1/2 AT squared. All right, let's see some problems. 3-kilogram watermelon is dropped off the Sundial restaurant in Atlanta. It takes 3 seconds to hit the ground. What's the velocity of the watermelon on impact? Well, what was the acceleration of the watermelon? 10 meters per second squared. If it takes 3 seconds, Vf equals Vi plus At. The Vi is 0, so A is 10, the T is 3. 10 times 3 is 30 meters per second. Negative. How far had the watermelon fallen by the second? Well, let's do our how far formula. How far formula. Our how far is delta x equals VIT plus 1/2 AT squared. We know the object was dropped, so we'll just do delta x equals 1/2 AT squared. So how far is delta x? The A is negative 10 because it's in free fall, and we were asked how far has it fallen in the second. So delta x equals negative 5 times 4, so delta x equals negative 20 meters. Straightforward. Number 3, how tall is the Sundial restaurant if it takes 3 seconds to hit the ground? Well, this is a very similar problem to the last one. It's a how far problem. Delta x, and really, let's use delta y, because now we're talking about up and down, equals VIT plus 1/2 AT squared. Again, Vi is 0, so delta y equals 1/2 negative 10 3 squared, because we were told it took 3 seconds for it to hit the ground. Delta y equals negative 5 times 9. Delta y equals negative 45 meters. How can the height be 45 meters? Negative 45 meters. Well, that's because what we're measuring is the distance and the direction. The watermelon went downward. Therefore, we're measuring the displacement of the watermelon with a negative number. What is the weight of the watermelon at the top of the restaurant? Well, the weight is simply its mass of 3 kilograms times gravity, which is 10, for a total of 30 newtons. But I think I left that question in accidentally, because that is our next unit. All right, so what are our assumptions for free fall? Free fall is when an object is only under the influence of gravity. So gravity is the force that causes the acceleration. We're assuming that there is no air resistance during free fall, so the acceleration is a constant 10 meters per second squared. And when the object starts from rest, the initial velocity will be 0, which will simplify our equations. Couple questions. When an object is in free fall, Does its velocity change by regular amounts, or does its velocity change by differing amounts? The answer is that it constantly changes by the same amount, 10 meters per second squared. That's because gravity is constant. All right, hopefully that was straightforward. Ask me questions if you have them in the live session.